Hi folks, this is Professor Mughal. Welcome to another tutorial. And this is a very interesting one because we are going to learn about the push button. If you look at your Basis 3 board, or for that matter any FPGA board, most boards are comprised of selector switches, the push buttons, 7 segments. We're going to focus on the push buttons because of the mechanical nature of these push buttons. When a push button is pressed on a board, you may think you have pressed the button once, but because it's mechanical in nature and it goes through several contacts while making that transition going from 0 to 1, their multiple signals are generated and they go back and forth. Okay, so I want you to focus on this red rectangle right here. This is the idle mode right now. When the button is pressed, you see the signal bounces between low and high several times before it is stable. So you may think you have pressed the button once, but the system may think that you have pressed the button more than one time, and that may cause an error into a digital system. Now this is where debouncing push button comes in, and it's a really handy thing to do because it can help you avoid a glitch in your digital system. There are several ways of coming up with a debouncing a push button, but this is one of the ways. Okay, you can do it many other ways. So what you see over here, you have a slow clock. We have a Basis 3 board which has a frequency of 100 megahertz. We are going to cut down that frequency to 4 hertz. The clock will be going to these D flip-flops, so the clock is being provided synchronously. Here is your push button right here, and these are the D flip-flops. So the property, the characteristic of a D flip-flop is because it's a positive edge triggered clock, every time the positive edge of the clock arrives, whatever is the state of the push button will go past and will be reflected at the Q1. So say if when D is 1 and the clock edge is arrived, Q1 will be equal to D, and because D is 1, so Q1 will be 1. If D is 0, clock comes in, Q1 will be 0. So that's pretty simple, right? Now I want you to focus on this timing waveform right here. We have this slow clock right here, and because it's a positive edge triggered, so it only look for a change in the state when the logic goes from 0 to high. Also, because we have a slow clock which is 4 hertz, so time being a reciprocal of 1 over frequency, you are looking at 0.25 seconds or 250 milliseconds, meaning one complete cycle which contains the positive half wave and the negative half wave. You're looking at 250 milliseconds, so you're basically slowing down the clock. Now the output of the Q of the first D flip-flop, here is the output which is Q1. Initially the push button is 0, so it stays 0. Once it reaches the positive edge triggered clock right here, the logic is still 0, so it stays 0, and it's going to stay 0 until the next positive edge of the clock arrives. And here it looks for the push button signal which is high right here, so it goes to high, and it stays high until the push button signal is high. And once it reaches this cycle right here, this part of the clock where it makes this transition going from 0 to 1, again the push button signal goes to 0, so it makes a transition from high to low, and then it stays 0 because your push button signal is 0. Then you want to look at Q2 bar. Okay, now one thing that is interesting here is when the clock pulse arrives, and say if the push button is pressed, meaning D is 1, so Q1 gets 1. But for that signal push button to arrive at Q2, it's gonna need additional clock cycle. Why? Because when the push button is pressed, meaning D gets 1 here, Q1 gets 1, and now it's gonna need another clock when Q1 becomes D, and D is then reflected onto Q2 and then Q2 bar. Okay, so if you look at your Q2 bar here, which is going to be the complement of Q2. So Q2 is basically Q1, right? Because Q1 is gonna input it into D, and then D is going to be eventually gonna be Q2 when the positive edge of the clock arrives, and then Q2 bar is going to be complement of Q2. So if you look at the output Q bar right here, the complement of 0 is going to be 1, and here it changes from 0 to 1, but because the output reflected at the Q2 will require 2 clock cycles and not 1, so there is gonna be it changes to 1 to 0 after 2 clock cycles, 1 and 2. So it goes to 0 here and stays 0, and then you see the Q goes to 0, and because there's a delay of 1 clock cycle because of this D flip-flop right here, it goes to 1 after a delay of 1 clock cycle. Okay, so basically Q2 bar right here is a complement of this Q right here with a delay of 1 clock cycle. And I explained that why there's a delay, because if push button is pressed, meaning D is 1, that 1 is going to be reflected over here at the Q2 after 2 clock cycles. Okay, so and then we have the single pulse output, which could be an LED in our case. What we are going to do in this experiment is when we press a push button, it should light up an LED. The output Q1, the output of the first flip-flop, and the Q2 complement of the second flip-flop then go into an AND gate, which then make a single pulse output. So meaning you're looking at this these two timing waveforms, and you're applying an AND gate logic. And notice here, the logic of the AND gate is when both inputs are high, the output is high. And this is what happened when the inputs were high, the output was high. So single pulse output, when the push button is pressed, it just gives you one single output. You don't see this erratic behavior in your output signal, which was the case when you were not debouncing the push button. So whenever the button is pressed, the logic goes from 0 to high. It waits for the positive edge of the clock to arrive. Once it arrives, it goes to 1 and then goes to 0. Okay, so this is the basics of the debouncing push button. We're gonna do that, come up with a Verilog code for it. We basically need 3 modules here, one for the slow clock, one for the D flip-flop, and one would be the top module putting everything together. So let's get rolling, guys. We'll start with the slow clock first, and I have already gone ahead and got our code ready. I'm just gonna go through it real quick because this is something we have done it many times in some other tutorials, but I just want to comment. So this is our input clock of the basis 3 board, which is basically 100 megahertz, and then clock out, this is going to be our clock, the 4 hertz slow clock right here, and then followed by, I'm going to use a variable called count, and I'm going to set the initial value to 0. How did I come up with this number right here? Again, I have explained it in my other tutorial, but I can just quickly go over it. So notice, you got 100 megahertz frequency from the basis 3 board. You want to convert it, cut it down to 4 hertz. So if you take this number right here, 100 megahertz divided by 4 hertz, so you're looking at 25 million cycles. Okay, meaning this is one complete cycle right here, one positive half wave and the one negative half wave. This is one cycle. there are 25 million cycles that would make up a frequency of 400 Hertz. And because each cycle contains positive and negative, so if I divide that by 2, you are looking at 12.5 million cycles. That means for the 12.5 million cycles, the logic is going to be set to 0. And then once we reaches that, so we're gonna use a counter which will start counting from an initial value of 0. Once it reaches the value of 12.5 million, it will reset itself to 0 and invert the clock. So say if the clock was high, it will go to low. And that's how it will create a slow clock with a frequency of 4 Hertz. So coming back to our coding, this hopefully, yeah, this number will cover this range right here, 12.5 million. So basically what it is, if you 2 to the power 25 equals a number which is greater than 12.5 million. Okay, I'm also gonna register my output clock as a register, and then we're looking at the positive edge of the clock, input clock. Whenever the clock arrives, the positive edge, the counter goes up by 1. Whenever the counter equals the value of 12.5 million, that is when the counter reset itself to 0. And after that it just inverts the clock. Okay, so this way for half of the cycle it will be off, and for the half of the cycle it will be on. So this is our slow clock right here. I'm going to go ahead and save it, and then run synthesis, make sure everything goes all right. It may take a few seconds. Just make sure everything went all right. We're not going to worry about the implementation part, but we are now going to move on to the Verilog code for the D flip-flop. So let's get started. The coding for the D flip-flop is very simple and easy, and like I mentioned before, the property and the characteristic of the D flip-flop is whenever the positive edge of the clock arrives, your next state is going to be the present state. So say if D is 1, Q1 is going to be 1. If D is 0, Q1 is going to be 0. So that's pretty simple. Let's do the coding for it real quick. I actually went ahead and did the coding myself. I'm just gonna go through real quick. So if you look at the block diagram, you got 2 inputs to D flip-flop, push button and the clock, and you got 2 outputs, Q1 and Q1 bar, or Q2 or Q2 bar in this case. Okay, all right, we got 2 flip-flops, so we're gonna make one, and then we, in our top module, we are going to instantiate these 2 flip-flops. Okay, so input clock. Okay, and remember this is a slow clock. Okay, we got the input D, this is the push button. Okay, we have the output Q and output Q bar, and we are going to register, declare them as register because they are going to be storing the values. Whenever the positive edge of the clock arrives, this is when the Q gets D and Q bar gets the complement of Q. Okay, so very simple coding. I'm gonna go ahead and save this as well and run synthesis on it. Just make sure that everything goes all right. Awesome, perfect. So this was successful as well. Now we got the slow clock now, and we got the D flip-flop. We are gonna work on our third module, create a third source file which will basically be the top module, and we're going to put together and come up with our digital system. So let's do that. And I think the best way to come up with the code for this debouncing push button is to think of this top module as a block diagram right here, and I'm just going to insert a box right here, this right here, and I'm going to So like no fill here, and also red. Applying. Right. Okay. So to the left of this box are going to be our two inputs. One is the push button. The other one is going to be the clock. And then if I like, I can actually stretch this box to over here, and then move this push button right here. Yeah. So our two inputs are going to be the clock of the basic 3 board, push button, and the output is going to be the LED. Okay, and everything we are going to instantiate the two D flip-flops that we created and the slow clock right here, and then we are going to assign a function to this output using the data flow modeling. So let's get started with the coding. I already got my push button input and my clock in as an inputs, and I got the LED output also. Anything that connects the two flip-flop, it can be declared as a wire. So the slow clock that comes out will be declared as a wire. Q1, Q2 bar will also be declared as a wire. So let's go ahead and do that. So I'll say wire clock out and wire Q1, Q2, Q2 bar. Okay. I'm going to instantiate the slow clock. Make sure the name matches exactly with the how you named it. 4 words, and followed by the identifier U1. It's got two arguments: the clock in, which is the input clock of the basis 3 board, which is 100 megahertz, comma the output, which is going to be slow clock clock out. Okay, now let's instantiate the D flip-flop. Okay, followed by the name and then the identifier name. So I'll say D1 here. The input to that D flip-flop is clock, slow clock, and the push button here. Clock out, which is the slow clock, push button. The output is Q1 right here. The second D flip-flop, so I use the identifier D2 for it. If you look at the second D flip-flop, the inputs are slow clock and a Q1, and the output is Q2. So we have slow clock, which is clock out, comma Q1, which is this right here, because Q1 is going in, becomes the input of the second D flip-flop. So Q1, comma the output, which is Q2, right here, and then I'm gonna use assign function. Assign Q2 bar is going to be the complement of Q2, okay, and then the output single pulse output right here is going to be you have Q1 ending with Q2 bar. Okay, LED equals to Q1 ending with Q2. I can say Q2 bar. I think our code is ready. I'm gonna go ahead and save it. As I save it, you should be able to see the hierarchy right here. Everything appears under the module debounce, which is our top module. Okay, alright, let's go ahead, and I'm going to actually, I also went ahead and put in my constant file. Basically all you need is a clock right here, the clock in. Again, make sure these names right here match exactly with the way you have over here. If not, then you'll get an error. We have one input, which is the push button, which is right here. Okay, so this is your input push button. Okay, and then this is your output LED, which is the single output pulse generated when push button is pressed. So our constant file is ready. You got the output LED, the push button input, and the clock right here. Let's select our top module, which is debounce, and choose implementation. Click OK here. Let's go ahead and save, and it's gonna take few seconds. Okay, when the implementation is complete, you then generate bit stream. Click here, and again it may take few seconds. As you can see, the bit stream file has been created, and now it's about time that we need to program that bit file into our board. But before we do that, we need to connect our board to a laptop. So we click open target, make sure the power is on, click next here. Your board should then appear over here. You click next and finish the process, and the last step would be to program the device. Click program, and after it gets done, you should be able to see the implementation of your code on your Basis 3 board, basically pressing the center button on the Basis 3 board, and it should light up the LED. So let's see that. So notice the center push button right here. When I press this button, the LED will light up. As I press the button, LED lights up. Go. Remember, this is all happening at a frequency of 4 Hz. You're looking at 250 milliseconds. Okay. So this is how the push buttons work, and it's important for us to do the debouncing because of the mechanical nature of these components. The signal swings between 0 and 1 before it gets stable, but if we can do some trick with it, basically waiting for a certain amount of time and then outputting the signal, coming up with a single output pulse, that is what debouncing does. I hope you enjoyed this video. If you haven't already, please subscribe to the channel. Believe it or not, there's so much of effort that goes into the making of these videos, and one way you can appreciate it by subscribing to the channel. Please give me your feedback, and I shall see you guys in another video. Thank you for watching. Bye.